12. Yes, I'm recording now. So, all right. Yeah, so I was saying, so my plan today is to discuss homework number 5 because I graded homework number 5. You can find their grades on Blackboard if you uploaded your homework on Blackboard. But I think some of you had the trouble with this homework number 5. So then I decided to go over this homework number 5. So the homework number 5, it's about chapter 6, right? So it's gonna cover everything in chapter 6. But first, guys, do you have any question about homework number 6? So yesterday, we went over homework number 6. I think I solved exercise 1, 2, and then 3. Well, not all the questions in the exercise 3, but I think I did like the first number 1 and just number 1 in the exercise 3, I guess.
I had a question about when we were doing it. I was going along and I did 7.07 divided by 7.1. I ended up getting 0.995774648. I remember you ended up rounding it up a little bit. So that's what I'm supposed to do too?
Yeah, you can do that. Yeah, of course. It's up to you. Again, because of the answers, I mean, if you round up your answer, at the end, you're gonna get almost the same answer. The answers are gonna be very close. Okay, so it's up to you. If you wanna round up your answer, it's up to you.
Okay.
Okay, that's not a problem. Yeah. So, does anyone have like a specific question about homework number 6? As I said, I solved 1 and exercise 1 and 2, right? I discussed the exercise 3. I did, I think, at least the number 1. I can do probably, yes. Anyone? Okay. Yeah. I can do, let me see. I think I did number 1, exercise 3, but then I probably didn't discuss number 2 and 3, right? All right. Yeah. Okay. So what I'm gonna do, let's finish exercise 3. And again, 3 and 4 exercises 3 and 4 they are very similar. And then I will move to the homework number 5. All right. So, okay. So this is homework number 6. And as I said,
quick question about the last one. Am I incorrect that I switched the P and the Q basically? I don't have it with me. That's why I'm so annoyed. It was I think it was 64. 64 was the P, and then 34 was the other number. So what I did was flip it because you wanted to find out what was not.
Okay, so you flip the P and Q. All right, so okay, let's do that then. All right, so okay, so this is exercise 4. Exercise 4. So again, this is about section 7.6. So yeah, as we said, this exercise and exercise 3 and 4, there is no normal distribution. So that would be a binomial distribution, right? So if you don't have normal distributions, then you have a binomial distribution. Binomial distribution. And then, so what you need in a binomial distribution, you need the probability of success, P. So you need P, which is the probability of success. And the probability of success, P, that will be the percentage given in the problem. Like in the first statement, in the first sentence, you'll see your percentage. You'll see a percentage which is actually your P. That will be your probability of success. So in number 4, it says about 64% of the people who are murdered knew the person who committed the murder. So the P would be the 64%. That's your probability of success, which is 0.64. Then the Q, which is always 1 minus P. So that's 1 minus 0.64. So that's 0.36. All right. So I guess so we know how to solve 1 and 2. So let me just remind you how to solve 1 and 2. So for 1, it says, so we have 65 current unsolved murders. So 65, that will be the number of trials. So whenever you have a binomial distribution, we need to find your P. So that will be the percentage given in the problem. So here it's 64%. And then the number of trials, that will be the number after the percentage. So the number of trials here is the 65. So N, number of trials, or the size of the sample, that's the 65. All right, so let me just say a couple of words about number 1 and number 2, okay, before moving to before discussing 3 and 4, all right? So for number 1, it says, well, find what's the probability that at least 38 of the victims knew their murderer. So you need to find the probability that at least 38 of the victims knew the person who committed the crime or the murder. So yeah, so again, guys, just to remind you here, at least, so that's like the minimum, right? So the minimum is 38, right? So then you need to find the probability that the minimum number of successes is 38. Okay. So again, the success, that's when the victim knew the person who committed the crime or the murder. Okay, that's a success. That's why I call it success. So when I say at least 38 victims knew the murderer, so then the minimum number of successes is 38. So we are looking for the probability that R, again, R, that's a variable, that's the number of successes. So R, that's the number of successes. And you want R to be, so at least 38. So the minimum is 38. So then that will be 38 or more than 38, right? So R is 38 or more than 38. So that's R larger or equal to 38. So this is larger or more or equal to 38. Right? So then we said in this case, so we want to find the probability that R, the number of successes, the number of victims who knew the person who committed the murder, is 38 and more, okay, or more than 38. And so in this case, we said because the number of trials N, see the number of trials N is 65, that's more than 20, right? And we said 20, that's the largest number of trials we have in the table number 2. So we cannot use the table number 2 to find this probability, right? Because here N is 65, that's more than 20. So in the homework number 5, guys, when we are gonna discuss the homework number 5, so the problems in the homework number 5, the N, the number of trials, they're gonna be less than 20. So if your N number of trials is less than 20, then you can use the table number 2. So in this case, 65, and which is 65, this is more than 20. And because it's more than 20, then we cannot use table number 2. So again, I'm gonna show you later when I discuss the homework number 5, how to use the table number 2, right? But here in this case, we cannot use this table. So the idea is, of course, we said we need to approximate this binomial distribution by a normal distribution. So we said in this case, so then we approximate. So the idea, so this is what we said in section 7.6. We approximate the binomial distribution by a normal distribution. And again, guys, the main distribution that we discussed are binomial and normal distributions, right? By a normal distribution. All right, so when we say normal distribution, if you can approximate by a normal distribution, it means that, you know, you are supposed to be able to convert your variable to the z, to the variable of the standard normal distribution. So in this case, our variables are, that's the number of successes. So first, we're supposed to convert r to x to a continuous variable, x, and then from x, we can convert to z, right? So convert r to x, and then we convert x to z. Okay. Now, how do we convert r to x? So the thing is, so this is probably that r is larger or equal to 38. So the thing is, guys, again, just to remind you, so this is 38, this is your r. So r is more than 38. So more than 38, that will be the right side of 38. If you are more than 38, then you would be in the right side of 38. So you need to find the area to the right of 38, okay? Because r, this is more or larger than 38. But the problem here is that if you, you know, if you take the area to the right of 38, then 38, it's not included in this probability, because you see your r is more or equal, right? Or larger or equal. This is supposed to be more or equal to 38. So you want to include the 38 in this probability. So to include the 38 in the probability, you need to move the little bit the 38 to the left. So then when you take the area to the right, then your 38 would be included in your probability. And we move the 38 to the left by 0.5. So that's 38 minus 0.5, 0.5, okay? So that's how we include the 38 in our probability. So
Professor,
yes.
That's what I was confusing yesterday. Remember yesterday I was like 0.5?
Yeah, so there are two cases actually. So there is a case when you have like r more. So there are two cases. So if you have like r more than some number, like here it's more than 38, then when you convert to x, the continuous variable, so then you need to subtract. So x is more than 38 minus 0.5, because you want to include, that will be the area to the right, and you want to include the 38. So we need to move the 38 a little bit to the left. So
what vocabulary you would say it has to say, so you know when it's plus 0.5 or minus 0.5?
Yeah, yes. So when it's more, then that will be a minus. You need to subtract. When it's less, so when this is more or equal, right? This is more or larger, more or equal. So because it's more or equal, that's the area to the right, right? The area to the right of 38. Now, when it's less, so it's if you have like, let's say, r is less or equal to 38, okay? So this is less. This one here, it's less or equal. So when it's less, you know, you take your number line, right? You take your number line. This is, here's your number line. Here's your 38. And here's your distribution. Less than 38, that's like the left of 38, right? So you take the area to the left of 38. Okay, but the thing is, you want to include the case when the number of successes is equal to 38, right? So to include the R equal to 38, you need to move the 38 a little bit to the right. Okay, so then if you move it to the right and take the area to the left, then your 38 would be included. Okay.
So we will add.
You would add, yes.
Okay, that's
the plus, yeah.
Thank you.
So that's the difference. So in this case, you would have probability that X is less or equal to 38 plus 0.5. Yes, so that's like the two cases. Okay, does this make sense to you? So if you see the word more, okay, perfect. So yeah, yeah. So here we convert R to X. So because this is more, so we said if it's more, then we subtract. So that's X larger or more than 38 minus 0.5. So okay, okay, this is just a remark here. This is a remark. This is just a remark. All right, so yeah, let me write down again here what I just said. So this is R more than 38. So that's X more than 38 minus 0.5. So that's X more than 37.5. All right. So I convert R to X, the continuous variable. Now we need to convert, as I said, we need to convert. So now X to Z, right? I converted R to X. Now I need to convert this X to Z. And that's where we use, the normal distribution. And in normal distribution for the X, your Z would be equal to X minus mu over sigma. All right, that's how we convert X to Z. And again, guys, there's a difference between X and X bar. The X bar, the sample mean, if you have to convert X bar, then that would be X bar minus mu over sigma divided by square root of N, the size of the sample, square root of the size of the sample. So yeah, anyway, so this is how we convert X to Z. So then, so that's probably that Z is larger or equal. So we have, this is the value of X, which is the 37.5. So that's 37.5. And then I'm supposed to subtract, the mu, the population mean over sigma, right? Divided by sigma. And again, we said, like in this problem, you don't see any mu and sigma, right? There is no mu and sigma in this problem. But the thing is, this is a binomial distribution. And a binomial distribution, as we said, we discussed in the section 6.3, how to compute the mu and the sigma of a binomial distribution, right? So just to remind you again, guys, because this is a binomial distribution, then we know how to, so from section 6.3, so we know how to compute the mu, supposed to be n times p, and the sigma, that's supposed to be square root of n times p times q. I think we computed this yesterday, right? So like here, n is again 65 times p, the 15%, sorry, the 64, I said 15, 64%, the 15, that was exercise 3, yes. Exercise 4, it's a 64%, so it's 0.64, right? Okay, so I have the answer for exercise 3, but I don't have the answer for exercise 4, so I'm gonna just try to compute this thing here. So times 0.64, so that will be equal to 41.6, okay? And here, it's square root of 65 times 0.64 times the Q, and as we said, Q, it's always 1 minus P. It's right here, the Q, it's 1 minus P. So it's 0.36. So this is times 0.36. 0.36. Right? So then the sigma, so this is times 0.36, and then square root. The answer point would be, it's 3.86. So if you round up, I guess that would be 3.87. All right, so what I'm saying here, guys, that so this mu is actually 41.6, and this sigma is actually 3.87. All right, so then this is probability that Z is larger than, so we have 37.5.
Sorry, Professor, R is
yes.
sigma?
Say again.
R equals sigma?
No, R is not sigma.
Oh, okay. I thought you said
R. No. R is the number of successes.
Oh, okay.
R is actually equal to square root. You see this square root of, and under the square root we have n times p times q.
So how do we find the sigma again?
Yeah, it's right here. The square root of n times p times q. The
n times p times q is sigma.
Yeah, the square root. Yeah, is the square root of that.
Okay.
Okay.
N
So
times p times q, do the square root, and that becomes the sigma.
Mm-hmm. So okay, yeah. Mm-hmm. Okay, let me give you more details here, I guess. Yes, with the computations. So what I'm saying is, so sigma is square root of. So you multiply the 65. That's an n. This is n. This is p, and this is q. You multiply n by b by p by q. So that will be 14.976. And then you need to take the square root of this 14.976. Okay.
All right, so I wrote down sigma is square root of n times p times q divided by the square root.
No, it's not divided. You apply the square root. So you multiply, you multiply 65 by 0.64 by 0.36. You get the answer, which is 14.976. And then you press the square root function. Then you have to apply the square root. Okay.
Okay.
So when you apply the square root to this 14.97, the answer should be like 3.87. I don't know. Do you have your calculator with you, or? I mean, you can try it.
Yeah, I have my calculator, and the tutor showed me how to put the square root in with the n over d with the fraction thing, and then you hit second, and then you hit x2. Like you obviously, you have to put your, your formula in at the top, and then when you get to the bottom, you hit the down button.
Okay, so your square root is a second function.
Yeah.
In your okay. Then you have to press the second function. Yes. Yeah, of course. Yeah.
Which was helpful because I Googled the square root, and it was completely different than what the calculator gave me. Like, for example, I did the square root on my phone of 45. It gave me 6.70820. But when I did it on the calculator gave me 2.884527.691, which I rounded to 2.885.
All right, that's weird.
Yeah.
I mean, if you want, if you have time after the lecture or tomorrow, we can discuss. I can show you the. If it's up to you, of course, but I can show you how to use the square root of your calculator.
Okay.
If you have time, either today after the lecture. Either today or tomorrow.
That's fine.
Okay.
Thank you.
Just let me know. All right, guys. So we have your sigma, and then what I was saying. Yes. So we converted x to z. So we said we have z more than there is the 37.5 minus mu. So that's 41.6 over sigma, which is 3.87. All right, so again, this is mu and this is sigma, right? And then, you know, so this is probably the Z is more than, you know, you take the difference. That's negative 4.1 in the top and over 3.87. So this is Z more than, probability that Z is more than, Z more than. So negative 4.1 over 3.87. So that would be, I think, 1.0. So negative 1.05, right? And then one more thing, guys, as we discussed yesterday in details. So this is more. So this is area to the right, and this is the area to the right. And to use our table number 3, we need to convert or express this in terms of the area to the left. And we said area to the right, that's 1 minus the area to the left. So it's 1 minus probability that Z is less than negative 1.05. So less, that's the area to the left. Area to the left. This is less.
And Professor, when I just typed that into my calculator, I had just put in 4.1 over the 3.87, and I got you know, the same answer you had. But so I noticed I don't have to put negative, because when I try to put negative 4.1 over 3.87, it said sync error.
No, you don't have to put negative anyway, because you know, negative over positive, that would be negative.
Oh, okay.
You don't have to, well, you can put minus, like minus 4.1 and then divide by 3.87.
Okay.
Well, I guess if you try that, I mean, just put minus 4.1 and then divide by 3.87, that will give you a negative 1.05.
Because on my calculator it doesn't say negative, but it gave me the 1.05.
No, but then, well, when you subtract, like in the top, it's you need to start with 37.5, right? It's 37.5 minus 41.6. Because if you start with 41 minus 0.6 and you subtract 37.5, then you're gonna get positive. So I'm not sure if did you start with the 37.5 or with the
no,
0.1?
I didn't. I went from
the other way.
Yeah.
Okay. Yeah. Okay. Well, then that explains why you got lost.
So like, well, I'm doing it on a calculator. Say I was doing 37.5 minus 41.6 over the 3.87. The answer from that, then I just keep going on the calculator.
Yeah. Yeah.
Okay.
Yeah, you can do that. Yeah. Yeah.
All right. Because I haven't really been using this calculator. I was using my phone, but.
No, but be careful because of the PEMDAS rule. So when you subtract and divide, it's gonna do the division first because in PEMDAS rule, you know, the division comes first before the subtraction. So first, you need to, you know, subtract and then press like equal and then divide. Okay. Yes. So then, yeah, and then now you can just use our table 3. You know, as we discussed yesterday, that will be 1 minus, you know, etc. You're gonna get this probability from your table 3, and then you're gonna get your answer. All right. So I'm gonna now discuss. So this is for at least. So the minimum is 38. Now for number 2, it says, you know, for number 2, it says at most. So at number 2, we need to find the probability that at most 44 of the victims knew the murderer, right? So 44 knew the person who committed the crime or the murder, right? So at most means maximum, right? So maximum of number of successes here, maximum. number of successes.
And Professor, when we see at most, that means that's our standard deviation. Like, would the 44 be our standard deviation?
No, it has nothing to do with the standard deviation here. So when you say at most, this is just to say it's just to say that R is less or equal than 44.
Okay, because I know the homework 7.
Yeah,
I was looking, and when I was seeing at most, I knew that was my standard deviation in the question. So that's not all the time then.
Well, actually, I don't have the homework number 7 on my head. I don't remember, but I need to take a look to the homework number 7. But at most, in general, when you say at most, like, and there is a number after that, then that would be, it means like that would be the maximum. And so if you have your number of successes, here we're talking about the number of successes, then your maximum number of successes would be 44. Okay, but anyway, at some point you're gonna probably discuss the homework number 7, and I will see what you mean by the at most in the homework number 7. I don't think there's I don't know.
I was using it as like keywords to find my my standard deviation, to find my. Well, I'm not gonna tell you guys off because we're doing this.
But no. Well, anyway, later, I guess tomorrow, or not tomorrow, but next week when we're gonna do the review, we're gonna discuss homework number 7, and then just let me know.
Okay.
But here in this case, at most 44, it means that the number of successes is less or equal to 44. So less or equal to 44. Less or equal. Okay. So that's the difference between at most and at least in this when you have a binomial distribution. So again, at least the number of successes R is at least 38. So R is more than 38, more or equal to 38. And at most 44, number of successes R is less or equal to 44, right? Now, let me discuss the 3 and 4. So for number 3, it says more than 40 victims did not know their murderer. Right. So, all right. So here we need to be careful because the success here so in our case here, the success, when I say a success, I mean a victim. The victim knew the person who committed the murder, right? That's a success here. That's what we mean by the success. And so because the probability of success is, let's see here. So the victim knew the person who committed the murder, right? So then, so that's why the murder. So that's why our probability of success is P is, we said it's 64%. Now, I think I think someone said we can probably switch the P and Q. I don't remember exactly who, but yeah, I mean, if you decide, for example, I decide that the success is, now I'm gonna decide that this, yeah, oh yeah, thank you. So if you decide that the success is when the victim, let's say the victim did not know, right, the murderer. So in this case, the P would be, it's not 64, the P would be, of course, 100 minus 64, right? So the P would be 36%, right? In this case. And your Q would be 64. So yes, you can say, well, in this case, if you wanna solve or answer this problem where it says fewer than 40 victims did not know the person who committed the murder. So in this case, yes, you can, absolutely. That's actually good. That's one way to solve this problem actually, is to say, well, if my P is 36, Q is 64. So in this case, a success is when the victim did not know the murderer, right? So then here we are looking for the probability of R, the number of successes. That's when the victim did not know the murderer. So the number of successes here, it's fewer than 40. So R is less or equal to 40. Yes. But again, here in this case, when it's
and then we follow up with the same
steps. Same steps, yeah, absolutely. You can say, so your X, you convert to X. So this is less. So you need to add 0.5. And then when you convert to Z, so here you need to be careful a little bit, because when you convert to Z, 40.5 minus mu, but your mu, it's N times P, right? N is the same, which is a 60, where is it? 65. But P, it's not. So P, it's not 64%, right? P would be in this case 36. Okay. So here it's 0.36. So we're gonna have different mu. Okay, because so compared to the 1 and 2 here, when we decide that the success is when the victim knew the person who committed the crime, we said, when we computed our mu, where's it, mu? Here. So we multiplied N by P, which was 0.64. So we got 41.6, right? But now, if you decide that your success is that the victim did not know the person who committed the crime, then yeah, you're gonna get different mu, right? So just be careful here. So you're gonna get different mu. The standard deviation, however, is gonna be the same, because if you switch P and Q, it doesn't change the standard deviation. So this is, again, the same. So the difference is here. It's with the mu, okay? And then, yeah, so we're gonna get the same sigma, which is, where is it? Sigma was 3.87, the same sigma, but just different mu. So here, square root of, oh, sorry, we already computed this. So it's 3.87, we said. However, the mu would be different. So mu would be, so that'll be 65 times times 0.36, and that'll be 23.4. So here that would be 23.4 over 3.87. Yeah, so we can do that. Yeah, we can switch the P and Q, but just be careful. Of course, the mu is gonna be different than what we had before, right? So that's one way. That's one way to solve the problem, absolutely. The other way is just to take the opposite of the statement, right? The statement says like, where is it? So this is like the first, let's say this is the first way to solve number 3. To solve 3. The other way is just to take the opposite of the statement. So the statement says, so we have, so fewer than 40 victims. Did not know the person who committed the murder. So if you take the opposite of this statement, so the opposite of fewer would be more than. So this is more than. So the opposite, let me just write down here. So the opposite of the statement would be, so the opposite is, so fewer or less than 40 victims. So less or fewer, the opposite would be more, right? So it's more than, okay? And here we have 40 victims, right? But then if you take the opposite, you need to take the difference between your number of trials, which is 65, and this number right here. So if you have fewer than 40 victims, did not know the person who committed the crime, then more than, and then take the difference between, so number of trials, which is 65, and the 40. Okay, so 65 minus 40 victims. And then the opposite to did not know, so it's gonna be no. So they know, or they knew the murderer. Okay. So when you take the opposite statement, you change fewer to more, right? And then just be careful, this number here, 40. So then you need to take the difference between 65 and 40. Victims knew the person who committed the crime, right? So in this case, so R is more than, so 65 minus 40, of course, is 25. So we need to find the probability that R is more than or equal to 25, right? We do the same thing, but here mu is N times P, and P here is the 64%, right? So the P here, 65 times the 0.64, 0.64. 64, come on. So 0.64, and we said that's equal to, where is it? So, yeah, 41.6. So it's 41.6, 41.6 here. And the sigma is the same. Again, it just it doesn't change, right? So, yeah. Yeah, so in this case, so first, of course, to convert R to X. So this is more than, this is area to the right. So if it's the area to the right, then you need to move 25 a little bit to the left. So we need to subtract. So this is X more than 25 minus 0.5. This is more. And then, so this is X more than 24.5. Convert now to Z. So this is Z more than 24.5 minus mu, which is 41.6 over the 3.87. And etc. Right? Yeah. So that's another way to solve this problem number 3. Any question, guys? Let me see in the chat if there's anything in the chat. Okay, I got you, Edward. Thank you. All right, so this is for, oops. So this is for homework number 6. I mean, I think we already discussed in details this homework number 6. And if you have more questions, guys, just let me know, email me if you have any question about this homework. So as I said, we're gonna discuss now homework number 5, all right? So let's move to the homework number 5. And homework number 5, So this homework number 5 is actually covers chapter 6. Okay, so we have 2 exercises, 1 and 2. They are about sections. So exercises 1 and 2, exercise 2, they are related to the sections 6.2 and 6.3. And then there is a third, last exercise. It's about section 6.1. All right, so 1 and 2, exercise 1 and 2, they are about the same section. So what I'm gonna do, I'm gonna discuss the exercise number 2 because there are more questions. I think there are more questions in exercise 2 than exercise 1. Okay, so let's discuss exercise number 2. So this is exercise number 2, homework number 5. All right. So let me just read the question here. It says approximately 70% of all computer programmers are introverts. So in a group of 6 computer programmers, what's the probability that, etc. So as you can see, guys, from the question, there is no normal distribution, right? It doesn't, we don't have the word normally distributed or normal distribution, right? So if you don't have normal distribution, then it's probably just binomial distribution. So here we have a binomial distribution because there is no normal distribution, right? It doesn't say like X follows normal distribution. So this is a binomial distribution. And when we have a binomial distribution, then you will see there is like a percentage. So the percentage, that will be your probability of success. So like in the first sentence, it says approximately 70% of all computer programmers are introverts. So the 70%, that's your probability of success, right? So your percentage, the percentage you have, that's your probability of success. So probability of success is 70%. And then there is a percentage, which is 70%, and there is a number after the percentage. It says in a group of 6 computer programmers. So the group of 6, so we have a sample of 6 computer programmers, right? So the size of the sample or the number of trials is 6. So N, the size of the sample or the number of trials is 6. We have 6, a group of 6, a sample of 6 computer programmers, right? All right, so they see here a difference between the homework number 6, guys. The N is equal to 6. So N is less than 20. So this is, so the number we have here, 6, N, this is less than 20. Okay, so if it's less than 20, you can just forget about the normal distribution, what we did in the 7.6. We can actually use our, because it's less than 20, we can use the chart 2 or table number 2 to answer or to find the probabilities, okay? All right, so for example, I'm gonna just show you, you can just remind you how to do this, how to use this table number 2. So for number 1, it says exactly 3 of them are introverts. Exactly 3. So you need the number of successes to be exactly 3. Okay, so number of successes. So for number 1, you need to find the probability that the number of successes is exactly 3. Number of successes is exactly 3. So R, exactly 3. So you want to find the probability of R, number of successes, is equal to 3. So how do we do that? Using the table. So all you have to do, as I said, use the table number 2. Now, to use this table number 2, you need N. So to use the table 2 in this case, so we need the N. N is 6. You have a group of 6 computer programmers, and you need the P. Probability of success, that's the percentage you have, that's 70%, right? Which is 70 divided by 100, that's 0.7 or 70. So you need the N, you need the P. Now, And R is, your R is 3, right? You need exactly 3 successes. So R is 3. All right, so let's go to the table number 2. So R is 3, N is 6, P is 0.70. All right, so let's go to this table. So this is the formulas. Here's the table, table 2, right? So as you can see, first column, guys, N, you have N 2, 3, 4, 5, 6, 7. Next page, you have like 8, 9, 10. Next, it's 11, 12, etc. Right? And as I said, largest value of N is actually 20. Right? This is a last page of table number 2. So you see there's N 16 and then N is 20. And actually, it's not just, you know, well, so the largest N is 20, but there are also some missing values of N. For example, you know, between 16 and 20, you don't have 17, you don't have 18, or, you know, etc. So there are some missing values of N here. But anyway, but the idea is that largest value here of N would be 20. So then our N is 6. So we need to go to N equal to 6. So first column, again, 2, 3, 4, 5, and 6. N is 6, right? And then the next column, you have R. So next to 6, right? There is, next to 6, you can see there is 0, 1, 2, 3, 4, 5, 6. So we need to go to R equal to 3, right? Because the number of successes is exactly 3. So we need R to be 3. And then the P, probability of success, is 70%. That's 0.70. So you take a look at the top, the first row in the top, that's your P. So we have 0.01, 0.05, 0.10, 0.15, 0.20, 0.25, etc. But our P is 0.70 or 0.70, right? So 0.70 is, if you go all the way down to N equal to 6 and R is 3, the answer would be, what would be the answer? Any guess? N is 6, R is 3.
I could find it for you. You said N is 6?
N is 6.
Okay.
R is 3.
Okay.
And P is 0.70.
Oh, okay. Hold on. You said R was 6 or 4?
No, R is 3. N is 6.
Okay. I'm going over because I'm looking on my laptop.
Mm-hmm.
3 and then 6 and then 3.
Yeah, N is 6.
Did you say point? That's small. I see it though. I think it does that say 0.138. I can't see. On your screen.
1.85.
Yeah, sorry, it is 1.85.
Yeah, 0.185. Yeah, 1.85. Absolutely, yeah. So
take a seat, pal.
So yeah, so all right. Okay, it's gonna take a couple of seconds, I guess.
Yeah, because I know how to do that one. Before I didn't know how to read it. Now I know how to read it.
Mm-hmm.
What's helpful for me is like if I have a pencil and I'm doing homework, I circle my stuff and I line it up, and then when I'm done, I erase it.
Mm-hmm. Yeah.
That's so small.
Okay. Yeah, you can. Yeah, it's kind of small. Yeah, absolutely. I know. Yeah. So the answer is 0.185. So in other words, I mean, multiply by 100. That's 18.5%. Okay. So that would be the answer. So as you can see, guys, you don't need the normal distribution. You don't need anything. With the table, your N is less than 20. You can find, you can get your answer. Okay. Well, then there is number 2, 3, 4, and 5. Are there any specific, is there any specific question about this exercise number 2? I'm gonna discuss the 6, 7, and 8 because I think some of you had trouble with 6, 7, and 8. But does anyone have like a question about the 1, 2? Well, we just answered number 1, but what about number 2, 3, and 4, and 5? Does anyone have
with me right now? I don't have it with me, but I have a question.
Yeah,
There's
please.
no way that the answer will be more than a 100%.
Yeah, of course.
Case,
yeah.
right?
Yeah.
Okay.
Yeah. There is no way you get something more than 100% because.
And if you do, would it still be considered 100%? Because I remember you mentioned something that if it goes above a certain number, it will be, no matter what, it will still be 100%.
Yeah. So if it goes like above, well, that's like for the when you convert to Z, right? The standard normal distribution Z. If it's more than 3.49, we said that will be 100%.
Yes.
And if it's less,
Okay.
And if it's less than negative 3.49, then that will be 0%. Yeah. But yeah, the answer is always, anyway, the answer is always between 0 and 100%, which is 1. Okay. All right. So what I'm going to do, I'm going to discuss, I guess, number 6, 7, and 8, and because I think I got a couple of questions about 6, 7, and 8. So first, number 6, so for number 6, it says, so this is, again, this is exercise 2, number 6. It says, what's the expected number of introverts? Expected number, so, you know, expected number, that's your, the average, that's your X bar. So expected number, whenever you see the word expected, that's the average or the mean. So the expected number of introverts here, that's the sample mean X bar. That's what we mean by the expected number, the sample mean X bar, okay? Because by definition, the sample mean, that's the number you expect, you know, when you select a random, I don't know, when you select a random group, like here we have a group of 6, right? Yeah, so it's X bar, and so this is, so the sample mean or your population mean. So this is, so here we have, where is it? Sorry. So sample mean or the population mean. Let me just erase this here. So expected number, that will be your sample mean or the population mean. It depends on the context, of course, or the population mean, the mu. Okay. So again, the idea is that expected number, that's the average, that's the mean. So what's the mean here? Well, for a probability distribution, we said the mean, population mean. So we have a binomial distribution. So binomial, it's a binomial distribution. So we have a formula for the mu, the population mean, and we said it's n times p. So n times p, and we have a group of 6 computer programmers. So the size of the sample is 6, or the number of trials is 6. So n is 6 times the p, the probability of success p, that's the 70%, right? That's a 0.70, right? So when you have when you have a binomial distribution, guys, the expected number, that's the population mean mu, that's the average, okay? So in average, that's n times p, so that will be equal to, oops. So that will be equal to, I guess, 4.2. Okay. So what we're saying here is that, so in this group of 6 computer programmers, we expect that 4.2 computer programmers are introverts, right? So we expect that out of 6, we expect that 4.2 computer programmers out of the 6 are introverts. Okay. And And then it says, what's the standard deviation of this distribution? So standard deviation, we have a binomial distribution, and this standard deviation of a binomial distribution, of course, that's the square root of n times p times q. So yeah, so it's just, you know, square root of n, 6 times 0.70 times q, it's 1 minus p. So that's 1.3, okay? So the answer would be, where's my notes? I need to see my notes. Yeah, 4.2 times 0.3. So that's square root of, so sigma would be square root of 1.26. And the answer is, yeah, 1.12. Okay, because we have this binomial distribution, so you have your standard deviation, you have your population mean mu. Any question, guys? So again, whenever you see the word expected number, it means the sample mean of the population mean, right? So we have this binomial distribution, and we know how to compute the population mean mu. That will be your expected number. Number 7. It says, what's the probability distribution of the variable R?
I'm sorry, would you say, Professor?
Yes.
You said when we see expected that it's what?
So when you see the expected number, when it says like expected number, it says expected number. So what we mean is the mean. Like the expected number, we mean the average, the mean.
The mean. Okay, thank you.
In 7, what's the probability distribution of the variable R? Okay. I think, I mean, some of you answered this question like saying this probability distribution is a binomial distribution, but that's not the answer. Probability distribution, yeah. So probability distribution is, so what do we mean by probability distribution first? So when we say probability distribution, guys, we mean that we assign for each value of the variable a probability. So probability distribution means the following: we assign for each value of the variable. So here we are, our variable is R. The variable R, for each value of R, of the variable R, a probability. That's what we mean by probability distribution. So for each R, you assign a probability, right? So
Professor, are we supposed to write that, or?
No, that's not the answer. Here I'm trying to explain what do we mean by the word probability distribution.
Yeah, no, I remember because I put it's a binomial distribution. So yeah, instead I was supposed to put what you wrote.
No, that's still not the answer. This is just an explanation. I'm trying to explain what do we mean by probability distribution. So the answer would be a table. So here's the answer. So what we're supposed to do is to complete the following table. So here you have your R, the variable R. So values of R, number of successes, because we have a group of six computer programmers. So the number of variable R, the values of R, they go, they are from 0 to 6, right? Because we have a group of 6 people, right? So the number of successes are the number of computer programmers who are introvert it's actually from 0 to 6. So R can be equal to 0. We have 0 introvert computer programmer, or 1, or 2, or 3, or 4, or 5, or 6. So the 6, that's the maximum number of computer programmers who are introvert. So that's the all possible values of R. Wow. And for each value of R, we're gonna assign a probability of R. Probability of R.
Give it.
Okay, so this table would be that's what we mean by probability distribution. This is your binomial distribution, or probability distribution. So this is what we mean by the probability distribution. So we need to complete this table. So for example, when R is 0, so what's the probability that R is 0? Well, we have to use our table number 2, right? So we use table 2 to complete this, to complete or to find this probability distribution. So for example, when R is 0, so P, of course, it's 0.70. N is, we have 6 computer programmers. So if you check, if you go to the table, let's see here. So when N is 6, R is 0, and P is 0.70, then the answer would be 0.001. Okay, so you need to go to the column where P in the top is 0.70, right? 0.70, N is 6, R is 0. So the answer would be 0.001. So there, here should be, it should be 0.001. And then when R is 1, R is 1, that will be 0.010.
Come to the room, Chloe.
Mm-hmm.
Come on, so.
R is, yes. Is that a question for me? Probably not. Okay. So yeah, for 2, we have 0.060. For 3, we said we had 0.885. For 4, we had 0.324. For 5, we had, where is it? I lost that. Yeah, 0.303. And for 6, we had 0.118. Again, guys, how I got these numbers from the table number 2, you go to N equal to 6. So here's N, and then N is equal to 6. Next to 6, that's R. So we have 0, 1, 2, 3, 4, 5, 6. And then in the top, you have your P, and you go to 0.70, right? Then you go all the way down here to N equal to 6. Then that's where you find so this is where you find the 0.001. Here you get 0.001, and then you get 0.010, then you get 0.060, etc. That's where you get your answers.
Yeah, that's what I was doing, and I kept going down to get the next thing.
Yeah, the last one would be 0.118, right? That's so yeah, this table, that's the answer to the probability distribution. For each value of R, you give the probability of R. That's what we call a probability distribution. Any question, guys? Hopefully this answers your questions about this. All right. Yeah, absolutely, Annie, yeah. All right. And then let's see, what does it say next? So that's the probability distribution. Graph the probability distribution of the variable R. So for the graph, guys, just to remind you here for this, when you have we have the binomial distribution. So what we do, so the graph, it's going to be a histogram. So here you have your R, like there's 0, 1, 2, 3, 4, 5. Then the largest possible value for R is 6. And then on the vertical axis, you have the probability of R. Okay, so probabilities of R. So for example, we have the smallest probability is 0.001. So we need to plot, I guess, here somewhere 0.001. Next, we have 0.010. Just be careful here because the values, the probabilities are not increasing. Okay, they're not. Okay. Yes. So next value would be 0.010. next value. So again, guys, so the values are not increasing, right? So the next value would be 118. So where is it? No, sorry. Now next value, it's 0.06. Right, so 0.060. And then we have, so next value, it's not 185, it's gonna be 118, right? Because 185 is larger than 0.118. So next value here would be 0.118. And then we have 0.185. And then next value would be, well, it's not 0.324. It's gonna be 0.303 because 0.324 is larger than 0.303, right? So it's 0.303 and then 0.303 and then 0.324. All right, so then now for 0, we said the probability of 0 is 0.001. So we're gonna draw like a box around the 0. So what we do is we take the interval. So here we take this interval with center 0. Right, the height is supposed to be, it's supposed to be the 0.001. Next probability is 0.010 when R is 1. So we're gonna have like a rectangle right here. So the center of the interval is 1 and we need to go up to 0.010. So we're gonna get this box right here. 2, the probability of 2 is 0.060. So for 2, so we take the interval with the center given by 2 and we go up to 0.060. For 3, it's 0.185. So it's 0.185. So we're gonna go take the interval with the center 3 and we need to go up to right here, right? 0.185. For 4, it's less, I think 4 is, no, it's more, it's 324. So 4, the probability of 4 is 324, 0.324. So we're going to take this interval with the center 4, and we need to go all the way up to 0.324. Okay. 5, the probability of 5 is 0.303. So it's less than 0.324. So for 5 is going to be 3.303. So it's going to be up here, I guess, right here. And then for 6, last probability, which is 0.118, and that will be, take the interval with the center 6, and we need to go up to 0.118. So right here, I guess. Okay, so that's the graph. That's the graph of the probability distribution. So the idea, guys, is that, so, you know, you can take so the graph would be, you know, so this, if you take this, that will be the graph of your probability distribution, right? And the area under the graph, that represents actually your the probabilities of R. Anyway, so yeah, that's for the graph of the probability distribution of the variable R. Any question, guys? So yeah, so that's for probability distribution, the graph. Is there any specific question about this, either exercise 1 or 2? Because again, both are related to sections. They cover sections 6.2, 6.3. All right, so the idea here is that, So we have this binomial distribution, but in this case, the number n would be less than 20. So then you're supposed to be able to use the table to answer, to find your probability. Let me just say one word about, yeah, well, here again, in the, in the number, like number 2, 3, and 4, for example, when it says, let me just make a remark here. So like in number 2, it says, or number 4, it says, when it says at least two of them, so again, at least means the minimum is 2. So then the probability of R, that would be probability of R more or equal to 2. So at least that's the minimum, right? Minimum is 2. So then R is larger or equal to 2. Okay, so R is larger or equal to 2. And then like for number 5, it says no more than 3. No, that's a different thing. But yeah, so if you have like a question like it says no more than 2 are, let's say, introverts. So no more. So in general, no more means that the maximum. Okay, when it says no more, that will be the maximum. So this is the maximum is 2. Okay. So then that will be a probability that R is less or equal to 2. Okay, so this is less or equal. Okay. Yeah, I guess, all right, like we have like 3 minutes left. Well, the exercise 3, yeah, let me just at least say one word about exercise 3. So exercise 3 covers section 6.1. So in section 6.1, guys, the main formulas we had in section, so this is exercise 3. It's about this section 6.1. Well, as you can see, there's this probability distribution again. So we need to compute the probability of probability for each value of x. X, that's the number of kids. Right? X is the number of kids, and then so x is the number of kids, and then so the number of kids is from 0 to 4. So if you want to find the probability distribution, then you need to complete this table where we have like x and p of x. As I said, x goes from 0 to 4. So 0, 1, 2, and then it says 3 and 4. And then you have probability of x. So then you need to find the probability of x. For example, like a probability of x equal to 0. So here you select a random couple. We have 50 couples. Number of couples with 0 kids, it's 25. We have 25 couples with 0 kids out of 50. So that's like 25 divided by 50, right? So that's like half, 0.5. So the probability that x is 0 is 0.5. So again, 25, that's the number of couples with 0 kids divided by the total number of couples. We have 50 couples, right? Etc. So we are supposed to, to finish the table here. The graph, it's exactly the same as, the graph of this binomial. the binomial distribution exactly like this here. Expected number of kids. So expected number, as we said, when we have expected number, then we're talking about the mean. Right? Expected number, that's the mean. Right? And in this section, so this is not the binomial distribution, right? We don't have a binomial distribution here. So in section 6.1, we said when we have a discrete, where is it? So when you have a discrete probability distribution, then the mean mu, so mu is actually equal to the sum of x times p of x. And so we have this summation. And what we are supposed to do is, so this mu would be equal to, so you take the first value of x, which is 0, multiplied by the probability of 0. So it's like 0 times the probability that x is equal to 0 plus, because we have a summation, x is 1 times the probability that x is equal to 1 plus x is 2 times the probability that x is equal to 2. So again, this is section 6.1. X is 3 times probability that x is equal to 3, etc. So and then x is 4. That's a last possible value of x. So x is 4 times the probability that x is equal to 4, right? So for example, here, that would be, for example, here it's 0 times probability that x is 0. We said it's 0.5. So 0 times 0.5 plus, and then etc. So you have to, of course, we have to find the probability that x is 1, etc. All right, I guess I went over time. Yeah, so I guess I'm gonna stop here, guys. Thank you for listening. So as I said, you can think again about this homeworks number 5 and 6. And if you have again any question left, then we can probably discuss it next time. All right. Thank you for listening, everyone. And hopefully I'm gonna see you tomorrow. Take care, everyone.
Thank you. Bye.
Bye.
Awesome.
Bye-bye.
Thank you.
Thank you, everyone.
Oh, she would sit down. Make it real difficult.